Lots of thanks. Very good morning, good afternoon. And once again we try to understand some physics together. And actually today's lecture is mainly motivated and is based on a question that Sarah asked me after our third lecture last time, and that made me think, and I tried to work on this, and I think I will take almost full lecture just answering that. But it's a very fundamental question that she asked. It's a very beautiful, wonderful and very fundamental question. So her question concerns the construction of higher energy states, construction of higher Fock states, construction of Fock states, construction of n particle states. All these things are equivalent. Okay, and I think it's important in the sense that without knowing this, we really do not know what is going on. So Sarah wanted to know a few things which are answered after, which requires an understanding of the so-called Fock state. And the theory for this was developed by none other than Paul Maurice Dirac for bosons in particular, and by people like Wegener and Jordan for the fermions. And it's named or it's known by the name of the Russian physicist Vladimir Fock. So Fock space, and we will gradually know what it is. So this is about half a century old story when quantum field theory was getting developed at the hands of these people like Dirac, Jordan, Wegener and many others. Okay. String theory was not born there at that time at all. Nobody knew the name of string theory at that time. So it was the quantum field theory was growing and was being developed. The fundamental rules. So actually that is the basic. And whatever is applicable to field theory, its suitable generalization is directly applicable to string theory and to superstring theory also. So let me first try to address this question. You might recollect that once in a while I make this statement, or I might have made this statement, that in quantum theory we have the possibility of creating energy out of vacuum, okay, which is not empty but is a soup of boiling particles being created and destroyed. It's a very popular statement that I also like to make, and many others also like to make. But it has deep physics, and actually our today's lecture will be based only in explaining this. How you do it, what it is, and how should one attack it, how should one address it. So, and this thing is applicable right from quantum mechanics to quantum field theory to all kinds of quantum field theories, involving scalar, real scalar field, complex scalar field, vector field, Dirac spinor field, and so on. Everywhere it's applicable. And it's also equally applicable to string theory, which by that I mean bosonic string theory, as well as to superstring theory. Okay. So construction of Fock states. What is a Fock state? We try to see. This is a n particle state. So this is a general notation of a n particle state, where you have n k1 particles with momentum k1, n k2 particles with momentum k2, n k3 particles with momentum k3, and so on, n ki particles with momentum ki. And then, so we would define a number operator n ki which operates on nk1, nk2, nki equals to nki and k1 and k2. I'll make things much simpler in a few minutes. Okay, so don't be afraid of what is looking here. I could write it for short, and that would be an expression in just quantum mechanics. This would be an expression in field theory, but they mean the same. So this is a n particle state, and this is the number operator n, where n we would define as the product of a dagger and a, where a dagger is the creation operator and a is the annihilation operator. I'll come back to the simplest example, one-dimensional harmonic oscillator in quantum mechanics. Okay, but just to give you, so let me not write those two little more complicated looking steps. Let me already come to the simplest of the things. So let me start with a very simple example, one-dimensional harmonic oscillator in quantum mechanics, and we will see how it is being used all the way in string theory. So I would be random in my description from quantum mechanics. I could go to field theory or to string theory, but I would explain each and every statement, each and every thing that I write or I speak. Okay? If you do not understand, please do interrupt me and ask me. Okay? So let me consider one-dimensional harmonic oscillator. Things would look much simpler, okay, and they would hold true with very minor generalizations to field theory and to string theory. So let me write down the Lagrangian 1/2 m x dot square minus 1/2 m omega square x square. So I am just writing the Lagrangian for a one-dimensional harmonic oscillator, which has this parabolic potential. These are just constants. So you can plot. You can plot the potential. This would be the potential V equal to x square. Okay. This is the x, so very well known harmonic oscillator potential or the parabolic potential. If you plot it, V on this side and V equal to x square. Okay, so you have this, and these are kinetic energy in one dimension. Okay, all right. Now I follow the n particle state description or the Fock state description is useful in the so-called second quantization. So if we talk about second quantization, we also need to know what is first quantization. So what is first quantization? You start, whether if you are working in classical mechanics and going to quantum mechanics, or if you are considering field theory and going to classical field theory and you are going to quantum field theory. So the first step is you calculate all the momenta. So for example, P would be 1/2 into 2 into m into x dot m x dot. This would give me x dot equal to p by m, and with this I can go back to the so-called Legendre transformation, sigma pi qi dot minus l. This would be p x dot minus l minus 1/2 mx dot square minus 1/2 m over square x square, and this you can rearrange. This will be p square by 2m plus the so you obtain the expression for the Hamiltonian. But right now we are working in classical mechanics, classical theory. Everything here is classical, and in classical phase space we also follow Mr. Dirac, and what we do, we calculate the Poisson brackets. In all the phase space variables of the theory, there are only two phase space variables for this theory, x and p. Okay, so Poisson bracket is defined as and summation over k. Summation over k. Now you can calculate between x and p. So this would be del x over del x del p over del p minus 0 into 0, and this would be just 1. Okay. If I had xipj, then I would have xipj, then I would have it like that, and I would have a sum over k. In that case, I would obtain sum over k delta I k delta j k. This would be delta ij. Okay, it would be summed over k, right? It would be summed over k. So here for this particular theory, this is the only result. So you have x and p, and this Poisson bracket would be just 1. And if you calculate between x and x, it would be 0. Between p and p, it would be 0. So what we do in the so-called first quantization, we calculate all the Poisson brackets of the theory among all the phase space variables of the theory, vanishing and non-vanishing ones, and then we promote all the classical variables to quantum mechanical operators following the standard rules of quantum mechanics. And therefore this would give me x p bar equal to 1 would give me, so Poisson bracket is minus iota by x cross times the commutation relation. This is the famous Dirac quantization rule, which is applicable to mechanics. So this is a classical object, this is a quantum object. Okay, so if I write x and p Poisson bracket, this corresponds to minus iota by x cross times x p. This is the quantum mechanical operator. Commutation relation is a quantum mechanical operator. Okay. So on the one hand side, on the left hand side you have classical object, on the right hand side you have, and this is the famous Dirac quantization rule. If at some point of time I would be very happy to derive it, but not today. Okay. For when I do the time evolution operator in quantum mechanics, it's such a beautiful description. I was doing it for curiosity, just to discover how these so-called great brains work, and I was very happy to derive it on two sides and to get it, this equality. How, I mean, it's out of the blue, you cannot have this idea, so there must be something. So, but not today, some other time. Okay. Here, now I make, if we have said this, then this would complete the so-called first quantization. Okay? And then, what is the second quantization? Actually, the quantization procedure is not complete unless you have achieved the so-called second quantization. So, what is then second quantization? And there, this question of Fock space automatically would come. Okay? And particle state or particle representation would automatically appear. So what we do is we proceed to construct a. So let me just remove all this. Okay. So let me introduce x equals to h cross by 2 omega m times a plus a dagger, and p would then come out to be, I need to define only one, then the other would follow. So p would be iota times h cross m omega by 2 times minus a plus a dagger. Actually, this expression or this representation of expressing x and p as a linear sum of the annihilation and creation operator, which I would derive in a few minutes why they are called annihilation and creation operators. In terms of these, you can also call them Fourier modes. Right now we don't see them in quantum mechanics, but they would be visible as soon as we make a transition to field theory. So our purpose is we want to express x as a linear sum of a and a prime, a and a dagger, and p as a linear sum of a and a dagger. In field theory, what we would do, our x would be replaced by the field phi of x or psi of x or a mu of x. In string theory, this would be replaced by the string coordinate capital X of mu or psi of mu for superstrings psi of mu that we talked about last time. And on this side, you have multiple choices. I can have plane wave expansions, so multiplying them with e to the power minus ikx, e to the power plus ikx. Okay? In field theory. I'll write them down too. But we want to catch the logic. And similarly, we will do the same thing in string theory, identically the same thing in string theory. And therefore, if you like, you can invert these equations and you can solve these two equations for a and a dagger. So you will obtain m omega by 2h cross times x plus ip by m omega, and a dagger would be m omega by 2 square root 2h cross and x minus ip divided by m omega. So we originally introduced a and a dagger, some two objects which we would know later what they mean and why should they be called as annihilation and creation operators at all. But we right from the very first step, we say that they are operators. Operators means they are quantum mechanical operators. Okay, they would obey standard quantum mechanical rules. All right. If you can do that, then there are a few important things that we needed. You can calculate a product of, let us say, A dagger and A, and this would be, you can, I'm skipping the intermediate steps. This would be F by H cross omega minus 1/2, and that would give me H equals to H cross omega times A dagger A plus 1/2, or if I would now define it as N, then I would write it as H cross omega times N plus 1/2. Okay, and then so this is just a very trivial algebra, but what we have done here is we have used the commutation relations of X and P. Okay, for writing this down, you take this. So you take product of A dagger, and A is obviously two terms here, X plus IP, some constants, times F minus IP, some constant here, some constant here. So these are, you will get 4 terms, right? And they are now, as I say, they are operators. So X, X, P, X, X, P, X, P, P. Okay? So to simplify them, you make use of the commutation relation HP equal to IH cross. Okay? The commutation relation of HP, which is HP minus PX. Okay? Which is HP minus PX in IH cross. Okay? Very good. Now I would like to define an eigenstate. Okay? So how would I do that? I would like to define N, and I like this German notation, putting double dots before the equality sign, so I define it. Okay? I define this to be equals to N and N, and then this would immediately, I can derive N A dagger N equals to N plus 1 A dagger N A N N minus 1 A. These 3 equations are very, very fundamental. I define only one. Okay, then all other things follow. And what is this thing that I am defining? What I say is, let this I'm using the Dirac Bryant-Cat notation. So let this state N represent the eigenstate of this operator capital N, which is an A dagger A. Okay. So this is the eigenstate of this operator with eigenvalue this. Okay? That's my statement. This is the eigenstate of this operator with this eigenvalue, little n. Okay? In that case, I would find that just using simple commutation relations, okay, you can obtain this, because n is A dagger times A. Okay? So then this A dagger times this state n, this is the eigenstate of this operator with eigenvalue n plus 1. And this an is the eigenstate of this operator with the eigenvalue n minus 1. So what is happening that this guy is reducing the eigenvalue by 1 unit and this guy is increasing the eigenvalue by 1 unit. Okay? So very good. You can obtain further more insight into these things. Now where is this h? So if I apply this operator to this state n, so what happens? H cross omega n plus 1/2, and then this gives me h cross omega. Okay? Just I have used n operating on n to give me little n operating on the state vector little n. Okay? Then this you can write as En n, and these are your energy eigenvalues, h cross omega n plus 1/2. Okay? Now very soon we would realize that before I erase these objects from here, before I erase these expressions from here, I would like to make a statement that this in fact expressing x and p as linear sums of a and a dagger is actually so-called Fock space decomposition of these operators x and p. Here if these are operators on the right hand side, on the left hand side also have to be operators. So here x and p are also operators. Okay? And so this actually is the Fock space decomposition of x and px. Okay? In terms of, here we have put e to the power minus ikx or e to the power plus ikx as 1. Okay? So they are not carrying any momentum dependence. In a short while I will write this expression for, let us say, for a real scalar field theory, then things will become little more transparent. Okay? And but you see, this algebra would continue to remain the same, and here you have these energy eigenvalues. So you see, it's enough to define just this one step, that this is the eigenstate of this operator with this eigenvalue. Then all this rest of things you can convey, and then at the end what we want to do, so we want to obtain, so these are the energy eigenvalues. Hamiltonian is also an operator, and eventually you can calculate the commutation relations between A and A dagger, which will be 1 here in this case, and A would be 0, and A dagger would be 0. So once you calculate the expression for this is the quantized energy. You look, this n, we will shortly find what is this little n. This little n is a number which takes value 0, 1, 2, 3, and there is no upper limit on this. I will prove it just now. Okay? And that happens because without being told, we are considering a bosonic system. So here everything is bosonic, all the variables are bosonic variables, no fermionic. We will later on also consider fermionic oscillator. Okay? So a few things I might, and once I would calculate the quantized energy, and I would calculate these commutation relations for A and A dagger, etc., I would call that this would be second quantization. I would explain the physics behind it, okay? Little bit more, but algebraically. So that is it's a part of the description of the Fock space. So in Fock space, automatically this product A dagger times A, which represents the number operator, which we define as the number operator. This if we obtain its matrix representation, it would come out to be a diagonal matrix. Okay, I'll just now prove it. And here the n would commute with n. So these two properties, they go, actually one means the other. So it's only one property. If n is diagonal, then n is going to commute with n. Okay, you can very easily prove. N is, so n is a dagger a. So obtain a commutation relation of a dagger a with a dagger a. So it's a commutation relation of a b with a b. And here a is a dagger and b is a, and you can make use of this last property, which also you can prove. So you can actually, everything follows from our basic definitions like this and this. And so matrix representation for n would be a diagonal representation. I can explicitly obtain this expression, and at that point of time people may not have realized, but you see, all these techniques, they are applicable all the way up to string theory and superstring theory. So this, okay, I might leave this for, okay, let me leave this. If needed, I can write again. So now just to give you an analogy here, let me write down this thing. I will come back to quantum mechanics again, but let me give you an example of a real scalar field theory. Okay, so this is defined by 1/2 d mu phi minus 1/2 m square phi square, and you then consider the Fock space decomposition of phi. So phi you can do one of the two. Twice omega k, a of k minus this plus a dagger of k e to the power plus I kx, and kx, here we need to know that kx is actually k mu x mu. It's a product of 4 vectors, so it's a covariant expression. If I write kx, it means k mu x mu, okay, which you can write k0 x0 minus, if you are using the metric plus 1 minus 1 minus 1 minus 1, okay. So and this could also be replaced by and I don't want to make a mistake, so let me h cross c square by v by correlation over k, and is this with a, yes, that's what I have been doing. There must be a square root. So I wanted to make sure if there was a square root here. So your first part in phi of x, this is called phi plus of x plus phi minus of x. Oh, let me speak a few words on this. This is called as infinite volume normalization, and this is called as finite volume normalization. So you can choose one of the two. Okay. Actually, the most standard books that I have been personally using for years, one of them is Louis Ryder, which takes, which always works in infinite volume normalization, and the other book, which is equally deep and thorough, is Mendel and so, and he always uses the finite volume normalization, but you can go from one to the other. It's possible to go this way, that way. All right. So this is just to establish equivalence to you, so that you read any book, but these are the only two normalizations that are in use. Okay. But of course, these are only plane wave expansions that I'm using. Okay, all the way up to string theory, we will make use of the plane wave expansions like that. But in principle, you can use here cylindrical waves, you can use here spherical waves, as you like. Okay, so there are further generalizations. I mean, you have more factors here, and this is for the real scalar field. So I have only one A and A dagger. So I have one pair of A and A dagger. If I write down its complex conjugate, for example, if I try to do that, then this term will come here, A, this will become minus of that, this will come here, A dagger, and this will become plus. Okay, iota becomes e to the plus AK. So by the definition, it is clear that this phi of x is a real scalar. Okay, but if I have a complex scalar field, then I would replace this by another symbol, let us say B dagger, and then its complex conjugate would be different. So I would have B, I will write it again. Okay. Now, but here the only logic that I wanted to give, you can see an analogy of this extension of this beyond quantum mechanics. What we did in quantum mechanics, we said this equal to 1, this equal to 1. Here we did not have explicit dependence on the momentum, right? But this was a linear expansion of. So here, in any case, in quantum mechanics, you will have a sum and not an integration. Okay? All right? So that is what we had in harmonic oscillator, one-dimensional harmonic oscillator. But here, then, so this is what is called as the positive frequency part. So this always contains an elation operator. Okay? And this is negative frequency part, and this always contains a creation operator. Alright? Okay, so then, and this along with that, without saying, it is always implied that this by this end, let me better use this symbol. Actually, I prefer this. So I put any expression between this, it means it's normal order. So you can see, if I have phi plus here and phi minus here, then, and I want to do normal ordering, then this would be phi plus has a, this has a dagger, so it would be phi minus, phi plus. Okay? And it's also clear because these are bosonic variables. If these phi's were fermionic, as for superstring theory, these phi's would be replaced by some Dirac spinor fields, Majorana spinor fields in 2 dimensions. They would be fermionic, and so let me write it. It is, I am making a mistake. It is just a product. It is just a product of the two. Okay, there was no bracket. I am sorry, it was a slip. Okay, you can tell me. So if I have psi plus times psi minus, then after I have written epoch space decomposition for the field psi, and after identifying positive and negative frequency parts, if I were to write the normal order product for this, then this would be minus 1 into psi of minus, psi of plus. Okay? And this would actually also mean, these two would also mean that if I were to write a dagger, normal order product of this, then this would be plus 1. I am writing on purpose a dagger A, Supposing I have some operator C or D dagger, then this would be -1 D dagger D. So this is for a boson, this is for a fermion, this is for a boson, this is for a fermion. Is this okay? So whenever you write the normal ordered products, and also in field theory, also in string theory, also in superstring theory, right from the definition of your action, Lagrangian, all the way up to whatever you do, without saying at each and every step again and again, it is assumed that everything is normal ordered. Okay, so normal ordering has to be done always. Okay, and so with this normal ordering, actually it has its relevance with the vacuum, and so you basically measure quantities relative to the vacuum. That is the idea. Now, if I can make use of this, and let me just replace this first step by a complex scalar field where my L would be d mu phi, either star or dagger as you like, times d mu phi minus m square phi star phi. Okay, so if I have this, then I would simply make it B dagger. Okay, and then all these things would remain the same, but I would have additionally, so if this is my phi star, now you take its complex conjugate, or if you like B dagger, so this is B of K times iota goes to minus iota minus IKX, and plus this would give me a dagger of K, and this would give me, because I have two fields now, phi and phi star, therefore I will have two separate Fock space decompositions, right? Is this okay? So after, and here of course I mean these applications would apply to whatever fields you are considering. Okay, so for example for this they would also apply to B dagger B. Okay, so if B dagger B here is B dagger would be plus 1 times B dagger. Okay, all right. Fermionic fields I will consider a little bit later. Okay, so this we need to know, and now let me come back to quantum mechanics and to real scalar field theory. Then things could be easily generalized and understood. Okay, so two things I am taking simultaneously. I am talking about quantum mechanics, which is one-dimensional harmonic oscillator only, and here in field theory it's an infinite collection of, or a collection of infinite number of harmonic oscillators, if you like. Also for the real scalar field theory, also for the complex scalar field theory, and the same for the string theory and the superstring theory. And we would demonstrate it. Okay, I will keep telling, all my entire story would be completely coherently related. Okay, and I would be answerable for each and every point. All right, so I think we need to talk a little bit on yes, here this definition actually this definition would get generalized of Poisson brackets. So if I have a field A of xt b of by t, and you calculate, so you call it equal time Poisson bracket, and we would calculate equal time commutation relations. Unequal time commutation relations lead to propagators. Okay, this we might not be discussing, but if needed I will come back. So equal time Poisson brackets, so how would you define them? No, summation over k, yes. And if I have ai bj, then summation over this. So del ai over abc del, let me see. So this is a function of, no, this is a, this is zt, but I can put a subscript k here. Let me better leave this page here, so I depend only on my mind. This is xt del b of j by and t del of instead of b, let me, okay, let it be, I wanted to write, let me change it a little bit, okay. Let me write it for, instead of a and b, let me write it for 5x of t, 5, and here I let you put I and j, pi of t, and this is equal time Poisson bracket. So t here t and here t, they are the same. Okay. So this del of 5i x of t and del of 5k z of t del of pi j by of t and del of pi k z and t minus del of phi I x and t del of pi k z and t and del of phi j by t, and this would be del of phi k z and t. Okay. So here what would I get? This would be my listing, summation over k. This would give me delta I k times delta of x minus z. This would give me delta j k times delta by minus z. Dirac distribution is an even function, so even by minus z or z minus by would be the same, and minus these two terms, delta I k times delta x minus z delta j k delta y minus z, and this now I can sum over k. So this would be my delta I j times these two If you like, I can take both of them at the same time. I can take Z integration, I can sum over K. Okay, so then I would be left with delta Ik times delta x minus y and this, I'm sorry, this has to be 0. This has to be 0. It is not there. This gives me 0. This gives me 0. So it's not this. This is 0. Phi I is not depending on pi. Pi is not depending on phi. So these two partial derivatives will simply vanish. So it is only this. Now if you like, I could afford to reduce, to keep my, for one more minute, and then I would integrate over. So delta Ij would remain. Here this would be x minus z delta z minus y, and now I will have, so that should be correct. Okay, and at some later point of time I would make one more generalization of this definition for the string fields, string coordinates, capital X nu. Okay, not today. At some point of time we would make just one more generalization. So is this okay? So what happens when we are considering a real scalar field theory or a complex scalar field theory, at the moment just involving bosonic fields, okay, then we are in the first place starting with the action or the Lagrangian or the Lagrangian density. We are constructing all the Poisson brackets of the theory among all the phase space variables of the theory, and then promoting the variables, classical variables, to quantum mechanical operators. So Hamiltonian, also quantum Hamiltonian, okay, instead of classical Hamiltonian, and then upgrading your Poisson brackets to the commutation relations. That would complete your first quantization. And for the second quantization, what you would do, you would again go into the Fock space decomposition that we just now considered for phi or for phi dagger, and calculate all the commutation relations between A and A dagger, B and B dagger, between all of them. Obtain all the non-vanishing commutation relations, and the other ones will be the vanishing ones. So, and express the Hamiltonian in terms of the number operator or the annihilation and creation operators, A and A dagger. And then, so this would remain a common procedure. And now we will derive physics out of it. We will construct n particle states out of this. Okay, so you will understand the analogy of how we do it in quantum mechanics, which is a little bit easier to remember. There are not too many subscripts there, but just a simple generalization leads to field theory results. Okay, so but of course, as you move from quantum mechanics to quantum field theory to string field theory, the symmetries involved becomes more and more rich. Okay, so for example, at the level of classical and quantum mechanics, you have the conservation of energy and momentum. When you talk about field theory, like real scalar field theory, the simplest field theory, and which would be applicable to all field theories, then you have many more things. Like for real scalar field theory, charge of course would be 0, but for a complex scalar field theory, charge would not be 0. Charge operator of the theory, okay, which is a consequence of the gauge symmetry of the theory. Okay, and in addition, there would be, you know, this famous equation del alpha t alpha beta equal to 0. So it leads to 4 conserved quantities, 4 components of the field momentum, field energy, and 3 components of field momentum. But you also have another 6 conserved quantities now in field theory. A little bit later I will tell you So like the components of angular momentum and the components of Lorentz boosts. 3 components of Lorentz boost, 3 components of angular momentum. In angular momentum including orbital plus spin both. So actually all these things, but when we write down just this, actually it defines each and everything about that. So when I am operating by, let us say, a dagger on n, then I am creating some higher states. We will see how. So if I have a vacuum state here, I am creating a one particle state by applying on it bunch with the creation operator. And in quantum mechanics, I would just write it like that. In field theory, I would write it like that. A dagger K. So either I would write it like this, or I would write it like, so this is one particle state. In field theory, I would write it, so this is my one particle state, and this I generate from the vacuum state. So this would give me 0. I'll show you how do we work it out. I did not plan to give a formal lecture on harmonic oscillator, but we make use of all its good and nice properties which are directly applicable in our field theory considerations. Okay, so and our main aim is still we are guided by one thing, that we want to understand the n particle state, construction of n particle state, construction of multi-particle states, or construction of higher energy states, right from mechanics all the way up to string theory, and what is their meaning. So actually this, now what would be this one particle state? When I am writing it down for a scalar field theory, then it would be a different content. But if I were writing this for a Dirac spinor theory, and if I would apply, so there I would have two kinds of operators. I would let me call this and this. So I will explain them to you later. So this or the dagger of R, K, and then this would be my this would be my one particle state, this would also be my one particle state. But in Dirac spinor theory, if this would be an electron state, one electron state, then this would be a one positron state. You can identify explicitly its spin angular momentum, everything you can calculate about this. So it's a rather vast thing. In many big conferences on various topics of particle physics or field theory, one very favorite question that Sarah had asked, but ours is a classroom teaching, we can afford to do it in details. People immediately jump on you. How about higher Fock states? What about higher Fock states? This is exactly trying to understand the many particle or states or multi-particle states. You apply it once again with CR dagger, you would have a 2 electron state. Whether it vanishes or not is a different thing. It would vanish actually. I will show you. If I were doing fermionic oscillator, then they would follow these rules. But if I apply here D dagger once again, then I would have a 2 particle state. There would be 1 electron and 1 positron. But if I apply here with D dagger, or if I apply here with C dagger, then I would have a 2 particle state, and this would be identically 0. You cannot put 2 identical fermions in the same quantum state. Okay, we know Pauli exclusion principle, and it will come out. I will show you how to get it. So, but let me first complete the bosonic oscillator before I go to fermionic oscillator. Okay, so right now I am considering everything which is bosonic. Okay, except this I just mentioned that it is not so straightforward to visualize what was happening if I would apply a dagger, or in the complex field theory. Well, in complex scalar field theory you could have B dagger. which would be A type of particle and B type of particle. Here you can identify with them, let us say electron